Last time we talked about the absolute temperature and talked about the entropy. Later on in the afternoon, some students came and said, why do we go through such complicated arguments? Many of you have already learned in high school about the temperature and entropy. Why not just follow what is in the book, which starts with just saying there is a temperature, there is an entropy. Well, the difference is if you just want to know something about thermodynamics without going into the details, it's okay to follow the book. But if you want to become a professional scientist, then you have to learn more the details. For example, the absolute temperature is a very sophisticated 中文是我这是一个sophisticated 跟 subtle 都是一类的字，就是一个微妙的，是一个微妙的观念。For example, we have said that a mercury thermometer does not exactly measure the same temperature as an alcohol thermometer. And when you go to very low temperatures, for example, you cannot use either mercury or alcohol. They would freeze. So you have to change to another thermometer. And the joint, there's a question of when you go to lower and lower temperatures, different thermometers present very large differences if you just use the usual calibration. So therefore you have to have some absolute definition. And when you get to such a situation, or when you want to have very accurate measurements of the temperature, then the concept of absolute temperature becomes essential. In any case, the definition of the absolute temperature and the definition of entropy are great triumphs in the history of physics. If you want to know something about the spirit of physics, you have to learn these sophisticated concepts. In fact, the reason that Einstein was able to make those revolutionary changes a century ago was because he followed the two traditions of physics. One is electrodynamics. The other is thermodynamics and statistical mechanics. Because he learned these two areas, he learned the tradition of these two areas very thoroughly. That's why he was able to make these revolutions. For an ideal gas, we know PV is equal to nRT. R is the gas constant, N is the number of moles, R is the usually in terms of energy per mole. Now this is always true. And we have dE is equal to dQ minus dW. That's the heat input into heat energy input into the system, and that's the work done by the system. And this is the increase in energy, increase in E. So the increase in E is equal to the work, to the heat energy input minus the work done. So this is the first law. And that is always true. For a reversible process, we have dq over T is equal to ds. So we substitute this into that equation, we get d is equal to T ds minus P dV. But we talk about the ideal gas. For an ideal gas, E is equal to CVT. This is in general not true. This equation is true for. So for a reversible process, we get d Cv dt is equal to Tds minus P dV. But P is equal to nRT over V. So we get Cv dt over T is equal to ds minus nR dV over V. If we integrate both sides, we get Cv log of T is equal to S minus nR log of V plus a constant. Or in other words, entropy is equal to minus n, sorry. This should be n, because the Cv is the specific heat per mole. We have n moles. So here's n is equal to minus nR log of V minus Cv log of T plus a constant. Let us take some examples. We had discussed this case once before. If you have a gas on one side and vacuum on the other side with a door which is closed, and you open the door, gas escapes that side. Now in this case, there's no we have d is equal to dq minus dw. In this case, you don't put it's insulated. Therefore, dq is equal to 0. Or we should say delta q is equal to 0. Work is 0 because it's not pushing any pistons. Therefore, delta E is 0. In other words, in such a case, there is no energy change, but the energy is equal to it's NCVT. So delta of NCVT is equal to 0. That means T final is equal to T initial. In other words, for an ideal case like this, it will just expand without changing temperature. So originally it's here. It has the same temperature. It doesn't. So we can draw an isotherm. So this is the initial state. This is the final state. I drew a dot 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 because it does not go from here to here through this line. It's you cannot draw because in the intermediate state, it's not. It does not follow any of these equations in the middle. We only know the beginning and the end. And you see that the entropy has increased because the fixed entropy curve follows the dq equal to 0. The fixed entropy curves are like this. Fixed entropy means ds is equal to 0. ds equal to 0 means dq is equal to 0. So it's s is equal to constant, and that's the PV gamma equal to a constant. So it's like this. So these curves are curves of equal s. So here's one s. This is the final s. And you see the final s is larger than the initial s. So in such an expansion, the temperature for an ideal gas, the temperature does not change, but the entropy increases. We know that it cannot go backwards. And that is an example of the second law. The entropy would increase, but it cannot go back. If it were able to go back, the entropy would decrease, but that's not possible. Let us write free expansion of ideal gas. 这就是刚才我们讨论的。The energy change is 0. heat changes 0.另外一个 let's deal with a second example. Second example 是个 box 里头有些 gas， 我现在在这儿摩擦，我会发生什么现象？在那个情形之下，这个 work friction on wall of gas. 那当然那个 gas 就变热了你如果把这个它的有一个它的 energy 是要 increased， 的 temperature 要变大了。那么它的这个是这样，你 if you include 这个外边这外边这个东西在这动来动去的整个这个system，它是 net by work convert and heat， 所以这个他所做的 work 是 negative 的。我想这个我想这个我不要这么，我 consider 一个东西放在上面掉下去，这个 system 是本来这个 gas 加上这个一个重的东西在上面，然后这 finally 变成这样了。我们来问这个 system 这个改变是什么？那么整个这个 system 的 total energy 是没有改变，这是 conservation of conservation energy。它的这个整个的 heat 呢也没有变，整个的work 呢是有一个 work， 为什么呢？因为地球吸了这个 body， 所以呢这work 是 negative 的。W 是 work done by the system， 现在是 work done on the system by the earth， 所以是 negative 的。而这个整个的这个 entropy 增加是大的。 为什么这 entropy 增加大了呢？因为它从一个 temperature 变成了另外一个 temperature， 在同一个 volume， 所以在这个图里头呢，它是在同一个 volume， 这是 initial， 这是 final。Any questions? Yes?
刚刚那个 delta E 的时候记了那个重力数，然后 delta W 的时候又记了地球的风，这样。刚刚这个地方 delta E 它不等于 delta Q 减 delta W 了。刚刚那个 table 上。
delta E。对 ，sorry， delta E 是negative， 你等我想想啊，这个it's good， 这个 E 啊，在这个 case 的话，我们的 E 这个 delta E 啊，应该是 E internal of 这个 gas。加上 E potential， 这个东西是等于0。这是 conservation energy， 可是这个是一个 positive quantity， 所以这是一个negative quantity， 所以加起来是对的。sorry， 这个是我们写 delta E 等于，我们说 delta E 等于 delta Q 减去 delta W， 这个 E 是得 total energy of the system。我们现在的 system 是包括了这个 body， 所以这个 equation 是这样的。而这个 system 是 conserve energy， 可是这 delta 这个是 negative 的。所以这个delta E 是 positive 的，所以 delta E gas 是 positive 的。那么而这个 delta E gas 呢，是要等于 delta Q 减去减去 delta W， 这个是 positive 的，这个是 negative 的，所以是对的。所以在所有这些 consideration 里头，得要 to start with 讲清楚你所讨论的 system 只是这个 system， 比如说是这个 gas。周围的东西你算不在里头。当你说是整个的 entropy always increase 的时候，是把所有的有改变的东西都算在里头，它的 total entropy 是 increase。What we discussed was a heat engine which draws heat from a high temperature reservoir and delivers a work with some remaining heat discharged at a lower temperature. That's what the principle of all engines. What we have learned yesterday is that for a given initial temperature, given final temperature, there is a maximum work that you can get out of it. and that in fact serves to define the absolute temperature. Now if you reverse that, it becomes a refrigerator. So what happens is that there's temperature T1, there's a temperature T2, and you do work. When you do work, it doesn't matter at what temperature. You do work with a Q2 absolute value, and that gives you Q1. So for example, T2 is in the room, T1 is the outside. The room is cooler than the outside, and you feed the refrigerator, you feed heat into the refrigerator, or the refrigerator draws the heat from the room and mix that with some energy, usually electric, and delivers it to the outside. So every refrigerator has something in the outside which expels the heat, and that amount of the heat, that amount of energy delivered outside is equal to the work done plus the amount of heat removed. In other words, Q1 is equal to Q2 plus W. There is a constant called K, which in some sense is the effectiveness of the refrigeration. And it's defined as the amount of work that defined as the amount of heat that's removed divided by the for a unit of work, you want to know how much heat is removed. But Q2 over, so we write as Q2 over Q1 divided by W over Q1. Q2 over Q1 divided, this is T2 over T1. W is 1 minus T2 over T1. So it's equal to T1 minus T2, T2. This means that if T1 minus T2 is very small, it's very efficient because this denominator is very small, so it becomes very large. What that means is that if you turn on a refrigerator and the room temperature is very little different from the outside temperature, then for 1 unit of electrical work, it removes an enormous amount of heat. The reason is because when the two temperatures are about the same, W becomes very small. So a very small amount of W would transport a large amount of heat. In fact, if you watch your refrigerator bill, you know that when the outside temperature is relatively low, close to the inside temperature, your bill becomes very little because your machine is working very effectively. Now for a real gas, we have these isotherms. These are no longer hyperbolas. These are two different temperatures. So they are not exactly hyperbolas, but this generally still is the shape. And the fixed entropy is also different from the usual one. So here is T1, this is T2. T1 is bigger than T2. And this is entropy 1, this is entropy 2. Entropy 1 is bigger than entropy 2. So for a real one, it's still like this. But we do not know in general the exact equations for the gas. Thermodynamics was formulated sort of during half a century in the middle of the 19th century. But before thermodynamics is completely and in a streamlined way formulated, already there was Maxwell, Boltzmann, who said that the reason there is thermodynamics is because there are molecular motion. And in particular, Maxwell invented or created the idea of the Maxwellian distribution. And that started a new discipline in physics, and that's called statistical mechanics. So statistical mechanics is the atomic view of why there is thermodynamics, or molecular view of the origin of thermodynamics. This is a subject which greatly developed in the 20th century, and it's one of the very important fields of physics by the end of the 20th century. Now we cannot go into that in detail, but I would like to give you some general ideas about what are the type of things that one discusses. So in particular, let's ask why Maxwellian distribution. What is a Maxwellian distribution? It says that there are different possible energies for the molecules. And the question is, what is the probability of the molecule having each of these energies? So the probability is equal to e to the minus beta ei. Times a constant. In other words, you have several energies, E1, E2, E3, E4. And there are particles which are in E1, particles which are in E2, particles which are in E3, particles which are in E4. And the question is, what are the relative weights, the relative numbers? And this is the Maxwell formula. The probability is equal to this. In other words, the probability, relative probability, is an exponential minus beta EI. The beta turns out to be 1 over kT. Why? Okay, first, if we have n particles, then the total number of particles is fixed. So we have summation of Ni. Second, the energy is fixed. When they collide, the energy is fixed, or when they exchange energy. So the total energy is fixed, and that's equal to summation Ni EI. There are Ni particles with energy EI. So the total number of the total energy in the I state is Ni EI. When you sum that over all I, you get the total energy. So now we have a problem. So let's give an example. Let's take a very simple case. E1 is equal to 1, E2 is equal to 2, E3 is equal to 3, E4 is equal to 4. In some units. Let's assume we have only 4 states. In Maxwellian distribution, you have an infinite number of states, but let's do it with 4 states. So these two equations become total number of particles is equal to N1 plus N2 plus N3 plus N4. That means there's N1 particle with energy 1, N2 particle with energy 2, N3 particle with energy 3, N4 particles with energy 4. Then the total energy is equal to N1 times 1 plus N2 times 2 plus N3 times 3 plus N4 times 4, right? So we have these 4 numbers, N1, N2, N3, N4, and they have to satisfy these 2 equations. So 2 variables with 4 equations. In general, you have many solutions. So let's just give some examples. Let's take this case. For example, suppose you have 8 with the lowest energy, 4 with next lowest, 2 with next lowest, 1 with the next lowest. You add these 2, you get 15. The energy, if you just compute it, it turns out to be 26. Okay, but that's not, we have two equations for 4 unknowns, so there are many possibilities. So I'll just give you a few examples. 9, 3, 1, 2. 10, 2, 0, 3. 7, 6, 1, 1. All of these have the same total number and have the same energy. Now, if you have 15 particles, you divide them into 4 groups. One group with 8 other group with 4, another group with 2, another group with 1. How many possibilities? Number of possibilities. Now you have all learned that in high school. So this is equal to 15 factorial divided by 8 factorial, 4 factorial, 2 factorial, 1 factorial. Okay, this one is 15 factorial divided by 9 factorial, 3 factorial, 1 factorial, 2 factorial, etc., etc. So relative weight. Let us call this 1. In other words, you take the ratio of these two, you find that this one is smaller. It's 0.44. So that means that you are more likely to find it in this distribution. This distribution is more likely than this distribution. Now you can do the others. But that's only with 15 particles. Let us now do it with 150 particles. And let us make this 80, 40, 20, 10. I'm just making every one of them multiplied by 10. So clearly the total number is 15 and the total energy is 260. And I take the next one, it's 90, 30, 10, 20. And this is again 150, 260. And here you would get 150 factorial, 80 factorial, 40 factorial, 20 factorial, 10 factorial. Here you would get 150 factorial, 90 factorial, 30 factorial, 10 factorial, 20 factorial, etc., etc. Now I can evaluate. You see that this relative weight is exactly the same as this. This relative weight is also exactly the same. But the probability is not going to be the same. If you take the ratio of these two, this one is 1, this one is 1.5 times 10 to the minus 4. So, when you have a large number of particles, the distribution here is going to be very peaked. In fact, if I do it with so that I have 1500 particles with the energy 2600, and I get 900 here, 300 here, 100 here, 200 here. It's again this, it's 2600. This number is extremely small. It's something like 10 to the minus 30. So it's essentially very, very small. Now in actual systems, you don't have 100 or thousands of particles. You get billions and billions and billions you get 10 to the 23 particles. So this is absolutely zero. So what do we learn? We learn that when you have a large number of particles, just the combinatorial distribution would make the distribution favor favor this one than this one. It's the law of large numbers. It's exactly like why everything has a tendency to become a Gaussian. So what is our conclusion? The relative distribution or the relative number of particles N1 divided by N2 divided by N3 divided by N4 is equal to 8 to 4 to 2 to 1, which is equal to, of course, 1/2, 1/4, 1/8, 1/16. And that's exactly the Maxwellian distribution. It's e to the minus epsilon times 1 divided by e to the epsilon it is e to the minus beta times 1 to e to the minus beta times 2, e to the minus beta times 3, and e to the minus beta times 4. Because where e to the minus beta times 1 is equal to 1/2. If you take e to the minus beta times 1 equal to 1/2, this is exactly 1/2, 1/4, 1/8, 1/16. So that determines the temperature. In fact, the beta is equal to 1 over kT. So we have proven in this case that the combinatorial formula forces the system into the Maxwellian distribution. What have we started with? We started with only two laws. One is the number of particles is fixed, n. The other is the energy is fixed, E. If the total number of particles is very large, then it forces it into one ratio, and that ratio is this one, and that gives you this temperature. So what we've just learned is the spirit of, in fact, it's an exact statement of how to get Maxwell distribution. But that spirit, when carried further, gives you the whole of the science of physical mechanics. And the first person who realized this was Boltzmann. So now there's an equation which is called the Boltzmann equation. Boltzmann equation is more general than Maxwellian distribution, and the statement is that the entropy is equal to k times log of probability. If you follow the spirit that we just had done, you eventually get this formula if you properly define what is meant by probability. This equation is now universally called the Boltzmann equation, and Boltzmann did have this equation in his mind, but he never wrote it down. He never wrote it down because Boltzmann was not a good expositor. He had all kinds of very complicated discussions, but Planck admired Boltzmann, and Planck wrote this equation down and said, this is my Boltzmann equation. And so today it becomes Boltzmann equation. And if you, as I told you before, if you go to Vienna, if you visit Boltzmann's tomb, there is a pillar, there's a marble pillar with his bust on top, and on it is written this equation. It is one of the most important equations. There are maybe only 10 equations which summarize the whole of physics, and this is one of them. Is everybody happy with this elementary, non-detailed explanation of the spirit of statistical mechanics? Now you may say, okay, starting from this, you are stuck with ideal gases, because the Maxwellian distribution that we are talking about was about ideal gases. If you are not stuck with ideal gases, because you can generalize the idea, and what we have done is for a non-interacting system where you can have a weak energy exchange, you would have this. But you can generalize this. After you generalize this, you get into modern statistical mechanics. And the person who did that was Gibbs. However, Gibbs had great difficulties, because when Gibbs tried to apply his ideas, Gibbs died in 1903, as I told you last time. And just before he died, he published a little book. And that book is now the Bible of 20th century statistical mechanics. But if you read that little book, you'll find that, in fact, I recommend that book to you. Borrow that book from the library and just flip through the pages. You don't have to go through the details, but it's like every student should have a copy of Luan Yu and flip through the pages, because just knowing that there exists such a book is of some use. But if you read that book, you'll find that in the introduction, Gibbs himself said that there's something wrong. Because while the statistical mechanics part of the thing he was very sure of, the result does not agree with experiment. It was later found that the reason that it did not agree with experiment was not because the statistical mechanics thing was wrong. It's because the mechanics was wrong. Because quantum mechanics was not invented yet. And in the 1920s, quantum mechanics was invented, so there was born quantum statistical mechanics. And with that correction of the mechanics, the spirit of statistical mechanics, which came from Maxwell, Boltzmann, and Gibbs, was exactly correct. And that is the state of affairs of statistical mechanics after that. And in this line of reasoning, there are even very important modern development, you probably have heard about it, called the Bose-Einstein condensation. What we have done depended on counting, was dependent on the combinatorial formula. The combinatorial formula in quantum mechanics has to be slightly changed. And that change in 1924 was first proposed by an unknown Indian young physicist named Bose. And when Einstein saw Bose's paper, he recognized that that counting is correct. But Bose was counting photons, light quantum. Einstein said that let's also use it to count atoms. That's a revolutionary idea, because the atoms were counted, had always been counted like what we just did. We had this n factorial that is typically from the classical counting system. Einstein said, let's follow Bose's counting system for the photons, but count atoms. So he got a different statistical mechanics. And from that statistical mechanics, he concluded that there is something now called Bose-Einstein condensation. However, at that time in 1924-25, people didn't believe him, thought he was completely crazy. But Bose-Einstein condensation was realized in 1995, and that won a Nobel Prize a few years after. Three people won. I think they won it in probably 98, something like this. Three people won it. One of them is Steve Chu. Steve Chu was a professor at Stanford. Now he became the director of the Lawrence Radiation Laboratory. Steve Chu's parents were both my classmates in Xinlianda. His father was a chemistry student. His mother was probably English, either in English or in history. I knew both of them not well, but I remember their names. So after, I didn't know Steve Chu before he got the Nobel Prize. After he got the Nobel Prize, one day I met him. So I asked him about his parents' names and verified that indeed both his parents were my classmates in Xinlianda. What this story tells us is that in the frontiers there are ideas and traditions that you have to learn. And you also have to learn what were the existing problems at that time. And then you have to have a judgment of, in order to search for a solution of the problems. For an important revolutionary resolution of a problem, usually it means you have to slightly change what has been accepted. And when you make that slight change, the whole field could be changed. And that is what Einstein was particularly good at. He repeatedly pointed out that what had been accepted was not correct and need be changed. And the changed ones, once you have understood it, in fact, usually is much more interesting and much more beautiful. Okay, I think with that we have finished thermodynamics. So we'll go into the next chapter. Electricity. Now the beginning of electricity is very simple. So we'll go through this relatively fast. It's what you have already learned in high school. There's Coulomb's law. Coulomb's law today is written in this fashion. Where epsilon 0 is equal to 8.85 . This is a unit, a coulomb. It's a unit of charge, which is defined in terms of amps. This is for the convenience of the people who do these very accurate measurements. And because of that, you get into this complicated form of the equation. But if you, the reason for this complicated form is because later on, things would simplify. This is Coulomb squared divided by Newton meter squared. Newton meter squared, Coulomb squared. This was published in a paper by Coulomb in 1785. I had looked at that paper. The experiment was extremely inaccurate. And in fact, it's very clear that it was not an experimental result. He guessed. He had data. The data is very inaccurate. If you just look at the data objectively, you cannot say it's like this. But he knew it had to be 1 over r squared because there was already Newton before him for gravitational field. So he guessed that it has to be this, so he published a paper. That paper, if submitted to a professional journal today, would be instantly rejected. Then nobody would say that he had any proof. So he was very lucky because people in general say that he discovered the Coulomb's law. Because of the Coulomb's law, since the force is 1 over r squared, attractive or repulsive, and you know, of course, equal charges are repulsive, opposite charges are attractive. And that's only a small difference between gravitational interaction and the Coulomb interaction. But because of that, the shear theorem, the two shear theorems of Newton work. That means if you have a shear, a uniform shear of charges, then the force, the electric force on a charge outside, say this is, there's a total charge of Q1 spread uniformly on a sphere, on a spherical shear, and there's a total charge of Q2 outside. Then the shear theorem says that the force between the two is as if this whole charge is concentrated at one point at the center. If Q2 were in the middle, it was inside the shear, then the total force on Q2 is equal to 0. These are the so-called shear theorems of gravity, and it obtains here too. Now, if I have a sphere, a metal conducts electricity, that means the electric charges on it can move freely. If I have a sphere and I put some electric charge on it, then because the different parts of charges repel each other, so they would try to expand, and the net result is that it would uniformly populate. It will uniformly populate the sphere. Does everybody agree with that? That is because of the repulsion, that is the best way to distribute it. You can ask, you might ask, okay, I accept that, but what happens when it's a irregular body? If I put a charge on it, then it would also be expelled onto the surface, but it's no longer uniform. It's uniform here because of spectrosymmetry. If it's like this, it's no longer uniform. For example, suppose it's like this. Then I think it's obvious because of the repulsion that there are the density of charges around here is small. The density of charges in these points are higher. After you study more mathematics, you would know how to solve this equation, and then you can prove, you can calculate the distribution. If it's an ellipsoid, then I think intuitively you will know that there will be more charges around here than charges around here. There will be charges all over the ellipsoidal surface, but the ends would have higher charges. Where the curvature is smaller, where the curvature is larger, there's going to be more charges. That's a standard equation. It is a standard problem in electrostatics. The interesting thing is that the mathematics of this problem is deeply related to the mathematics problem of the vibrating string or membrane. I have said that the wave equation for a string, the wave equation was y tt equal to v squared yxx. If you go to more dimensions, you get let's say d squared some function dt squared is equal to v squared Laplacian squared of f, which is v squared d squared f dx squared plus d squared f dy squared plus d squared f dz squared. This is the equation for a three-dimensional vibration. If you have only one, it's the vibration of a string. If you have only two, it's the vibration of a drum. If you have three, it's like the air vibration in a room. And this type of equation is deeply related to this problem. This shows that the mathematics has a certain uniform application in various aspects of physics. When people first started to look at the charges, we all know the charges that people first noticed was you have a spark in the winter time. If you rub one thing against another one, we all have that experience. And then in the 17th and 18th century, people began to play with it. You probably have seen movies. If you have something charged and you make a little girl standing on a charged stool, then her hair would stick out because the charges on her body tend to go to the end of the hair, and therefore the different ends would repair each other. So her hair would stand up. And in fact, this was a kind of a standard magic trick in Europe in the 18th century. And there were also the erroneous belief, 错误的belief, 以为if a person does that a number of times a day, it will cure her medical problems. In fact, if you go to Leiden, Leiden is a city in Holland, 荷兰的一个城叫做 Leiden. If you go to Leiden in the 18th century was a center of the study of electricity, and you still have very large machines which generate static electricity, and you have descriptions of the kind of magic tricks that were performed in those laboratories. So at that time it was thought that the electricity is a bit like energy, like heat. It can flow from one place to another one, like heat can flow. But in the 20th century it was found that there is a fundamental unit, and that was done by Millikan. In the 1910s, did the oil drop experiment. And found that electric charges are in integral units of a basic number E, and that turns out to be what was found is that they are electrons, and all the electrons have the same charge, E, a negative electron. There is a sign of E by convention defined, and with that convention all electric charge, all electrons have the same E with absolute value equal to this, but with a negative charge. And all positons have, all protons have the equal charge, but with a plus sign. And then in 1932, in 1930, it was predicted by Dirac that there is also a particle which is the partner of the electron, later called the positron, which has the same absolute charge but with a positive sign. And so we now know that there are many, many different particles, but all charges are in integral units of this number. Now, how about the quarks? Later on, well, in recent years, in the last, I would say 20 or 30 years, there's the idea that maybe there are smaller units equal to 1/3 of this, but no experimentally found 1/3 of charge has ever been discovered. There's something which is not quite understood here. So I would say the present situation is that experimentally the charges are always in units of E for all known experiments. There's a theory that in fact there are theoretical units of 1/3 of the E, but it would not exhibit itself in an experiment. That's called confinement. Around that, there are still, it's not controversy. There's still things which are not completely understood. So for you, I think the thing that you want to remember is that for all experimental results, there is a fundamental unit, and that unit is E. In the case of heat flow, there is no heat energy conservation. Energy is conserved, but you can create heat energy from mechanical energy. So the total amount of heat energy is not fixed. At the beginning, let's say at the beginning of the 19th century, people were unclear about the nature of electric currents. I told you once that one of the perhaps the greatest achievement of physics in the 19th century was the writing down of the Maxwell's equations. Maxwell wrote 3 papers, and I've studied these papers in detail. It turns out that he did not have the idea that charge has to be conserved, or at least he did not commit himself to charge conservation. Then in the middle of the second paper, he without explaining the origin of his thought, changed the equations and then derived the charge conservation. Did he make that change because he proposed charge conservation, or did he make that change and then derive charge conservation? It's unclear. That problem would require which was the origin, or which one came first, is something which requires more historic work. There are people who are digging up more letters between Maxwell and his contemporaries. So maybe one could find the answer to it. But whatever it is, he wrote down, he first said we need to add a term to the Maxwell's equations. And then he derived conservation of charge. Then he derived the velocity of electromagnetic waves. And then he said that since that velocity is approximately the same as the known velocity of light, so light is electromagnetic waves. And that, as I told you, is one of the great intellectual triumphs in the history of mankind. And its consequences for the 20th century is absolutely stupendous. So after that time, we all have the idea that there is charge conservation. It turns out that charge conservation itself has additional connotations. The principle of charge conservation has a lot to do with the structure of Maxwell's equation. From charge conservation, what happens is that it was pointed out in 1918 to 1919 that charge conservation is related to an idea called the gauge principle. And with the gauge principle, you would get Maxwell's equation. This was by Bayer. So in many senses, Bayer pointed out that the reason that they have Maxwell's equations looked rather complicated. But with this gauge principle, it turns out that it has some deep connection with conservation of charge. If you read Bayer's paper, this was very much on his mind throughout his contribution. It was very lucky for me that somehow it just got stuck there with very little further development. Then in 1954, Robert Mills, who died a few years ago, who was 4 years younger than I, collaborated, and we said that this is fine, let's generalize it. So we generalized this chain of a relationship. In other words, we generalized the gauge principle. And then you get new conservation concepts. And you could also say that you can start with a new conservation concept and then you get a new generalized gauge principle. It doesn't matter. Anyway, there's a new generalized gauge principle. And because of that, you then get equations which are generalizations of Maxwell's equations. And at the time, we were very lucky that in today's viewpoint, this is the most natural thing, and it was waiting for us to do. But somehow people didn't think about this. However, we did not immediately succeed, because although we wrote down the equations, the connection with experiment we could not establish. Then later on, in the 1970s or in the 60s and 70s, there was another idea generalized called symmetry breaking. So gauge principle plus symmetry breaking, that greatly flowered, and now it is universally accepted. So this development has won 5 Nobel Prizes. Various aspects of elementary particle physics, 2 experimental Nobel Prizes and 3 theoretical Nobel Prizes. So it's obvious that this generalized gauge principle which is deeply related to charge conservation originally. So it's related to additional generalized conservation laws, has something to do with the structure of the equations that determine fundamental forces of nature. So that's in some sense a very simple way of putting what elementary particle physics has achieved in the last 50 years. Okay, next time we are going to go more seriously into the structure of electric and magnetic fields.